So thanks everyone for joining us today. We'll start the session in 2-3 minutes. Let's wait for everyone to join and settle in. Hello and welcome everyone to another session in the Data R series. We are thrilled to be there with you this evening for a session full of action-packed learning. I'm Saubhagya Dubey, part of Analytic Vidya team. So for those who have joined us for the first time, a brief introduction to the Data R sessions. So the Data R session is a series of webinars that are conducted by Analytic Vidya and led by top industry experts. It is a fun way to understand the concept of data science and data engineering from the leading player in the industry. We are hopeful that these sessions are going to be great source of enrichment and value adding for our community members. So now on to our session today, which is a forecasting and time series analysis. So in this data, Varun will help us cover the basics of time series analysis, including popular R or Python modules like ARIMA, Exponential Smoothing, and FBprophet, as well as regression techniques. I hope you are excited for to attend the data with us. Before we kick things off, and I hand it to over our speaker, a quick recap of the housekeeping items. We are recording the session and recording will be available on our YouTube channel. The link you can find in the chat section. Please use the Q&A section for asking any questions you might have during the session, and we'll do our best to answer the following as the data progresses toward the end. We will keep sharing a feedback poll towards the end. You all are requested to kindly fill that up. And now on to our speaker. In the session of the data, we have Varun Behl with us. So meet Varun Behl, a data science engineer at Adobe in Bangalore, who brings these qualities and more to his role. With over past 5 years of experience in the field, Varun has worked with various types of data spanning industry, such as telco, e-commerce, pharma, retail, and web analytics. His expertise in the traditional modeling techniques combined with the passion for research has enabled him to make significant strides in the area of NLP, forecasting, segmentation, and recommendation. Varun is a highly skilled and innovative data scientist, always looking for new ways to push boundaries and deliver exceptional results. If you are looking for a data scientist who can bring fresh ideas and a wealth of experience to your team, look no further than Varun Behl. And before I hand it over to our speaker, there's a quick announcement that we are making this session live on YouTube. So please allow a minute to do so. Just a second. Okay, I guess it's on live. So thank you for your patience. Now over to Varun. The virtual stage is all yours.
Hi everyone, and thanks for joining the data series with Analytics Vidya. This is our fifth session of in which I have collaborated with Analytics Vidya on various topics catering to data and analytics. Um, we've covered some aspects of data wrangling, some aspects of outlier detection, recommendation systems, and all these content is available on Analytics Vidya's YouTube, as well as these are shared on their website as well. Moving towards the next series and the next session that we have picked for this session is time series analysis and forecasting. So although the scope of this entire topic is quite vast, so we'll try to cover as much as possible during this particular session. Let me quickly share my screen and we can get started. So, right. So today's agenda is time series and forecasting, as Sobhagya also mentioned about the topic. So we are going to capture basic elements of time series, and if time permits, we will move to the forecasting techniques. Although we plan to cover everything in this particular session, but if time doesn't permit, we probably will have another session where we will have an hands-on on the forecasting techniques that have been mentioned here. I do have a Python notebook also with me in this session where we will be walking through of the some of the techniques that are used to understand what a time series is and to make it fit for forecasting, and then understanding whether how these modeling techniques works. So moving to our first topic of today, time series and its component. Now, if you want to know about time series, it's just a random collection of data which are equally sequenced from at a time interval. These numbers could be anything from a sales volume, from a units metric, or a website traffic data. So any quantified value that is distributed over a time period represent a time series. Although we do not call every data time series, we want to make sure that it is intervaled at a regular periodic values and not at scattered or a random time space values, because then it reduces our purpose of doing any analysis and it makes it life very difficult to do that. Although there are various ways which we can tackle if the data is not evenly sequenced, we can probably roll up the data, like let's say the daily data is available and few missing data points come up. So we can obviously impute these values with various techniques that we've already discussed in data wrangling, like median imputation or mean imputation, or in time series forecasting we usually take a moving average of last 4 weeks to impute those certain values. But wherever the time interval is not equal, it makes life difficult to forecast. But although there are ways where we can aggregate data, let's say daily level data, the weekly level, or a weekly level missing data at a monthly level to at least make sense and get some trends out of the data and then do our forecast. Now, if you want to understand what are different types of time series that you might encounter when you are dealing with real life data, and even in our day-to-day life, what kind of time series data are getting collected. So there are trended time series where you might not see any kind of pattern in the data, but you might see in a particular direction in which the data is flowing. So I've shown an example of the mean surface temperature of Earth, how it is increasing over time. So that is a particular trend, but although it doesn't follow any kind of seasonality, at a very granular level, we might see on a day-to-day basis that there is some kind of seasonality. But if you look at the trend overall, it's just exponentially increasing trend and no pattern available. The second chart here represent the, like I've picked the data source of US natural gas consumption, and we can clearly see it's seasonal. So the reason of its seasonality basically comes out from that in the summer weather, the energy consumption usually increases, and that's why we see some spikes every year that the consumption of these energy resources increasing. And then there is cyclic time series data. Now, with this cyclic time series data, sections of it could be seasonal, but if you look at the data from an overall perspective, you won't see any seasonal or a particular trend that it is following. The most common example we see this kind of trends are in our stock markets, and the snippet here is of a Nifty 50 trend for last 5 to 10 years. And we see there are multiple contraction and increased spikes that keep on coming in the data. And the best way to understand data or like make any kind of prediction for this data is to not worry much about the historical, but more on the recent trends that are flowing in the data. So that helps us in picking these kind of data. Now, all these three types of the data can further be divided or from an understanding point of view into other three categories, which are autoregressive, moving average, and mixed time series. And when we are able to define them, that which category it fits in, it also helps us in solving the use case, that what kind of modeling technique we have to apply, whether it's good enough for forecasting or whether we need to do some adjustment to the data to at least make it fit for forecasting. Because at the end of the day, our goal is that we are able to make projections with that data, and it's close to what we anticipate would play out. So an example of an auto-regressive time series is a daily closing price of a stock. So next day, whenever a stock market opens, it always depends on what it closed at. So that's why these kind of data sets, we do not basically check for seasonality component, and we look at how last 10 weeks or let's say last 10 months have played out to forecast the next 2 months. And daily level trends might not match, but overall, in terms of the volume, it might predict the right thing. Now, moving average time series is basically, if you see the first graph here, also the 5-year running mean is taken. And that has helped us in at least smoothing out the entire trend, because now it tells you that it actually follows a trend. Whereas when you look at the spikes in isolation, it won't make much sense that which direction it's going into and what it is catering to. And a mixed time series is basically has both kind of component. Let's say there was a new product launch, it was showing a very high trajectory, and when the sales of a particular product saturated, then it started showing a seasonal trend. So it's kind of an example of a mixed time series. Whenever we deal with such kind of time series, it's better to understand from where the saturation or the stationary aspect of time series has started, and then from that point onward we uh, deal with the or use that kind of data. Now, moving towards what a time series is, what are the components of a time series or the composition of a time series, because they aggregate together and basically create a time series. So here, the example is just monthly unit sales of cars in America, and I've tried to drill it down to what kind of trends that we are seeing, seasonality we are seeing, and if there are any white noise or errors. So in terms of trend, if just a basic definition is like what's the long-term pattern in your data, you can visually see, and even through statistical means or plotting it, do you see anything, and it's usually monotonously increasing or a decreasing trend that we see over time. When we talk about seasonality, it's like some repetitive trend that you would might not be able to recognize when you see the trend as a whole. But if you closely observe, you might see that the troughs are occurring at a regular interval or at an equi-spaced distance from each other, which is basically a seasonal pattern. Although the volume could be increasing, but there is a seasonality angle available in this. Cyclical is a pattern that repeats at irregular intervals, and you might not see that. So we usually detrend our data or try to get our residuals out to basically see whether there is anything of that sort available in the data. This particular component of our data usually tends to deviate our model, and it's best to address these kind of cyclical patterns in your data so that the forecast doesn't have that in it. So if your historical data has a lot of cyclicity and it's basically adding to the residuals or the noise or error. All these three terms can be used simultaneously when we're talking about time series. So whether when these kind of components occur, it is going to hamper your forecast later on. So it's better we suppress them by any means. It's better to do some outlier detection on your data that trims off these kind of seasonal or non-seasonal trends, and it's better, will give you a much cleaner output from there on. Moving forward with the decomposition of the data, and what are the techniques and what are the techniques that are usually leveraged to understand what is the seasonality. There are a lot of ways by which we can actually extract these trends and seasonality in the data. And corresponding to this slide, I'll also have a demo of few techniques that I have just enlisted over here as well, and we'll walk through them, how different modules in Python can help you do this exercise quite quickly. And once you are done with this exercise, what you can infer from those data points and how it is now fit for your further forecasting exercise. So we usually have two types of decomposition techniques, and it depends on trend by trend or time series to time series. There are some multiplicative time series in which you will see that the seasonal component is proportional to trend, but both trend and irregular components change over time. So your trend is maybe it's increasing, then the increase is further more, and then it tends to decline. But seasonal component is proportional to that whenever that thing happens. So basically, whenever both trend and seasonality follow same kind of trajectory, then we say that there is a multiplicative ability in that particular time series. Whereas additive is a very simple trend. It's like you can create that time series by adding your trend component, seasonal component, or irregular or residuals in it. So as in the previous slide we discussed, we can segregate our time series into three different components. When these three components can be added together, it will be an additive decomposition. And if we are breaking them and then by multiplicative by product of these three components, we are again trying to recreate that trend, then it's a multiplicative decomposition. So both these techniques have been used, can be fit on, like one particular time series might be a good fit for both additive and multiplicative, because there are chances that over time some section of the time series was additive, and over time it started behaving like a multiplicative time series. So you can see that the trends might show both kinds of behaviors. Now again, I have this unit source data for electronic devices catering to AC, fans, cooler for XYZ company. Now, what we want to understand is what is the trend line, and we can clearly see if we draw a trend line by, let's say, just taking a moving average, we will have something like this flowing in, and it clearly shows us that it has an increasing trend over time. When we want to drive a seasonal trend, there are again ways of deriving our seasonal aspect. The best techniques that I use for my analysis is Fourier analysis. We fix a Fourier order. Now, if to give us some context around Fourier analysis, we try to fit our sinusoidal and cosine waves across a trend that it actually fits in that trend and is making a seasonal pattern out of it. So basically, the crest and the troughs of Fourier after doing the Fourier transform of that series, will actually fit in your seasonality pattern. So there are techniques of multiple techniques. Again, not just one is available to do that, but Fourier analysis usually is the best fit case. Other than that, for error component, what we do is, let's say we have our entire time series, we subtract the trend and we subtract the seasonality. So whatever noise that comes out from this particular thing, exercise, is our white noise or error component. The lesser the variance that we see in our error component, the better our time series is for forecasting. So if the error components tend to increase over time, make you can observe that when your forecast is also will underfit in those cases. Now, if I have to break down this kind of residual, I would say that this middle component has the least error and is less fluctuating, whereas the entire other components have a huge variance. So we have to address this error component in either way, in a way that the variance is reduced. We can probably add this residual component back to the time series, but we have to add it in a way by some smoothing technique where we reduce the crest and the troughs that are the spikes and the declines that are coming in the data. If we address these and bring them to a lower level, it's like the baseline zero level, then it's a good fit for our model, whatever technique we are going to try on. I'll reshare my screen and open the Jupyter notebook to show you the for the example of these decomposition techniques. So just give me a minute. So yeah. So there are certain modules that we should always like. These are the best use case models that I have even seen um, for complex exercises of related to time series as well. So you can always look up to these models. So sklearn, scipy, and stat models. These three basically suffice for every need that you need to run your forecasting exercises or even understanding a time series per se. So it's always a good exercise to preload these models. You can also go into the documentation of these modules, and I'll be sharing the notebook once post this session to even explain, like, and you can further deep dive into what these modules have. So they're basically catering to every statistical technique or machine learning models, traditional machine learning models that are out there, and you can use it on various kind of data for as per your need. So what I've done here, I've preloaded these few of these packages, and I have gone to upload the US FICAL sales data. I think I was even showing the same one in my the slides as well. Now it's the data is since 1976 and it's a monthly level data, so I'm going to filter it for the year 2010 only. And let's just also check how many rows item will be there, because that is important when we want to know whether it is a good enough sample size to even do some prediction. So we have 146 data points at a monthly level, so it's a good enough 10-year approximately data. Whenever you are running any time series model or anything, it's best to at least have 24 data points. So basically 2 data points for if you are doing at a monthly level. So it needs to cater into some kind of seasonality. If it's a weekly data, at least 14 data points are needed so that 2 weeks data is there and the third week can be predicted. So these are some nuances that is there with every time series forecasting, but usually a rich amount of data is available for most of the exercises. Now, what we are going to use here is the stats model package, which has a STL decomposition module already available. STL stand for nothing but seasonal trend laws method of decomposition. The back end of it again involves both multiplicative and additive ways of decomposition. We can even pick anything from Fourier analysis or moving average technique. It has the capacity to do it anyway, but there are certain default settings already been set in this particular package, and you can directly leverage that to see. So I have already, if you want to see the snippet of the data, it looks something like we have a date field and then sales field, and it's I think 10 years worth of data. So huge list of column till 2020 or 2021. I think the data range is available. So we need to have the data in this format where you have a date column and any metric KPI that you are measuring basically in a numeric integer format, because that's necessary to run any kind of time series analysis. And the rest of the work is actually taken care by this particular package, and you can drill down to these techniques. I have example of running Fourier analysis and moving average to find the trend and the seasonality below. But this is a package which is like one-stop solution to get the plots out of all these things. So the simple parameters that you have to give is to tell which model to use, whether additive or multiplicative. I've selected additive because I could see in the trend that there was very less uh, exponential increase in the trend, so might not have a very multiplicative behavior. So let's just try executing. All right. So this is our original trend value, and if you can see, it starts from 2011, has some kind of seasonality, which I can already see, but it again goes down. So the trend might not be unidirectional, the trend can be bidirectional, and we see a dip that probably caters to the COVID decline that had come in, and then again the second wave when it hit. So the sales of the cars obviously took a hit, and all these industries took a hit. So since then, it has not been kicked in, but this is like the original trend. Now if you want to, now the first thing that we'll take out of this is what is the trend look like, and this is the trend plot of it. And if you see, it actually saw an incremental growth till 2017, and from then onwards there was a saturation, and that's what the trend also shows us. And then there's a steep decline that's probably creating to the COVID impact that was there. Now, if you want to understand the seasonal component, you can clearly see it's stationary, like it's equal, not changing much in terms of the peaks and the minimas that are there in the data. So it's obviously in a particular range, and it's not, the variance of it is not high in terms of like the maxima and minima. But within that range, we can see some seasonal pattern flowing in every year. So it's obviously the car sales are seasonal. It's like some seasons, probably the festive season, end of December, are when people start putting money into these kind of stuff that they start purchasing. So that's why we see some seasonality in it. Now, if you look at the residual, again, it's very close to zero. So we can assume the data had very less noise till 2019. And obviously, the COVID period, it had the sharpest decline, which was not seen historically. So it's obviously something that didn't play out historically. And whenever it played out, we are clearly seeing a huge error in our data. It's obviously not an error. We can address it at the COVID impact, but to address it or to fix it, what we can do is we take moving average of these last 4 weeks and extrapolate these 4 weeks, and then help us in actually getting something closer to, if let's say COVID would have not happened, what have been the scenario. So that's how our trend would flow like. So on decomposition of data, you will obviously see these kind of plots, and how it will help in your analysis is that you actually know much more about your time series than you were knowing previously. So you know there is a particular trend that is there. You know the trend falls in some kind of section which you need to fix if you have to forecast the future. And seasonality point of view, it is fine. So you don't have to worry much about fixing seasonality or probably picking a period where the seasonality is visible. So sometimes what happens, the seasonality goes off in the recent stage, but it hasn't gone off. So we can still pick this data. Had it had gone off, we would have, let's say, picked the data till 2021 only, or omitted the part where the data was not seasonal. Now below is the example of, let's say, figuring out seasonality or a trend, cyclic trend or anything with using Fourier transform. So what I have done here is, and Fourier transform usually will provide you with a Fourier order, which is basically helps you in understanding that this is the number of sine waves and cosine wave needed to fit your plot or fit your entire crest and trough. So in in time series terms or analytical terms, these points are called change points. So it helps us in identifying what are the major change points in your data, and whether, and these change points, if seasonal, will occur again. So having this Fourier component, like the trend of Fourier component with you, is obviously important whenever you are forecasting. So I think this was already computed. So this snippet of code is nothing but I'm using the NumPy capability of Fourier transform. I'm passing my sales data as values and creating Fourier coefficients. The coefficients, there will be an amplitude to this coefficient, but some coefficients can be negative, some coefficients could be positive. So if you want to understand which would be the positive coefficient, wherever you are seeing spike from a baseline value, those will be always positive, and the ones which have a very lower volume, they'll have a negative coefficient. But we want to understand from an amplitude perspective, so we take absolute values from them. The phase is nothing but how, after how much time it is changing. So it's the NumPy capability of finding the angle between two data points is basically what it is taking. So it tells you phase of all these 146 data points from one point to another. So that is what is capable. Now, when I trend these with another functionality, that is reconstructing a plot, when I have all these values of amplitude, phase, and FFT Fourier transform coefficients together, and when I create a trend again out of it, and this equation is nothing but to recreate that particular trend, I will get something like this. And if you see, it almost superimposes on our actual trends, but it does capture some non-seasonal decline, and the amplitude is taken care of respectively. So what it will help you, or like moving forward, how this Fourier order or transform will help you is basically understanding that there is a seasonality component involved, but till what extent it has been followed. So I can say probably it has been followed till 2018 because I can clearly see that. And it is Fourier order also smoothens out your crest and trough, so you don't have to worry about that the peak might not occur or reoccur at the same time. So all these things are taken care of. Here I've just taken a Fourier order out of this. So I had actually passed the entire series in it. So that's why it's showing an optimal Fourier order of 99. Usually a very lower Fourier order also works well with a smaller data as well. Now, the other technique that we wanted to understand was basically figuring out the trend line, as we could see in the above chart also. But moving average or rolling mean is also a way of forecasting as well as identifying the trend in your data. So if I have, let's say I've taken a window size of 7, and for this particular data, it's like 7 months for 10. For a 10-year data, we've taken a moving average of 7, or let's say you can change it to 4 also. I think it should work. So when, let's say, we have a moving average of 4, we are actually able to map our entire data. The more we increase, the more smoothed down it will be. and it will help you in understanding the trend of your data. But this component is again important on helping on smoothing down your entire trend. So basically, if you are forecasting for your future, it's always better to do some moving average in experimentation, because it will make sure that the rise and the declines that were seen historically, maybe that might not play out in the upcoming future. So it's good exercise to smoothen your data or historical data before inputting into any kind of forecasting model. Right. Moving back to my slides, and we'll come back to this again. Yeah. So we had discussed decomposition of the data, and I hope I see there are a few questions, but I'd like to address them all at the last and collate few of the common ones which I can see already. Right. Now the next step that comes in, and I could see some questions around fitness of ACF and PACF. What are these terms and how do we leverage that? So the next part of our this session also caters to that only. So fitness of data for forecasting. This is, I feel, the most important step. No matter what technique you are going to leverage, it could be a sophisticated FBprophet model or an LSTM technique, which usually handle these kind of data anomalies well. But still, we want to have a cleaner data so that the forecast is explainable as well. It should not be that it's just a model generated output and we are not able to get any proper intuitive information out of that. So whenever we are checking for time series data, we first have to understand whether we want to do a univariate forecasting or it's a multivariate forecasting. So if your data only has a date column and a unit column or a numeric column which contains the metric that you need to forecast, then it's fairly easy that we can apply any techniques and go with the approach that we've been understanding, decomposing the trend seasonality and irregularities, and then reconstructing our trend line, and then inputting into any kind of univariate model to forecast the future. Apart from that, whenever we have multivariate data, we can have other parameters that are codependent on the metric that you are forecasting, but that's for later use cases that we will be discussing in this session. But for now, we'll be focusing more on the univariate time series aspect. So whenever you get a univariate time series, the first thing that we have to check is whether the time series is stationary or non-stationary. The reason for not having a stationary time series is that is the reason to not have your time series as non-stationary is that it will make your life difficult in forecasting. Non-stationary time series usually has a very high variance, high covariance within the data as well, and you need to do a lot of cleaning of your data to at least make it fit for forecasting, because it will show you trends that will not repeat in future. Those were repeated because of something played out historically, but it is not going to play out. And these kind of activities usually make your entire time series non-stationary. So again, your time series can have a stationary component as well as some time period within that time series could be non-stationary as well. But whenever we are dealing with it's best to clean all kind of non-stationary aspects of the time series. So yes, the basic meaning in statistical term of stationarity in a time series means that their mean, variance, and covariance doesn't deviate a lot over time. So if it is deviating a lot over time, then obviously it's not non-stationary, and you need to have a very sophisticated technique to predict. Stationary time series are very easier to forecast. You can use even moving average or basic growth run rate methodologies to even forecast these kind of stationary time series. I've shown three examples of non-stationary time series where we see the mean over time is continuously increasing. The variance has over time been changing, and the covariance has been declining and increasing over time. So this means that obviously the time series has a lot of complexity. So we need to have some way of reducing that non-stationary aspect of it. And the best way is to do some seasonal differencing, is basically taking some lag of your time series, some component of time series, and putting it as a difference the time to the time series window where you see those high variance or high covariance regions, and that will basically help you get to some extent of stationary. There are some statistical tests also available. You can visually also interpret whether a time series is stationary or not. But there are some statistical tests available which will give you a significance value whether the time series was stationary or not. And if it's stationary, you can go ahead with your forecasting. If it's not, then you might have to do some kind of imputation to tweak that. On the autocorrelation check, and I hope everyone would know that whenever we are running any regression technique, anything, there is a simple assumption that the series is not autocorrelate, or the metrics are not correlated to each other, and there is no autocorrelation between the variable also. Because most of the techniques like FBprophet model, it's also a regression based technique, just modified in a way that it can handle different seasonality components, noise component, outlier components. But the structure or the base of that is again based on our logistic or linear regression concepts only. So again, the autocorrelation, even in a time series, would make it difficult, because you can use a normal regression technique also to forecast. And if you have an autocorrelated metric in that, it will not help you generate a right forecast out of it. It would have a lot of overfitting in it. So there are few techniques to check. An ACF autocorrelation plot and partial autocorrelation function plot, both of them helps us in understanding how the seasonality looks like, and which model, let's say there are, if I talk about the basic forecasting model, uh, ARIMA and moving average model, whether they are a good fit or not. They can also be, you can also justify that from ACF and PACF functions. So I've shown a small example, and we'll move back to our notebook to see how these autocorrelation plot look like for the trend that we were discussing. And it's more or less like this, and whether there is some seasonality and how to observe that seasonality, and then how to take a call whether which model it will fit in. So by examining the ACF and PACF plots, anyone can identify the time series model. If you see a seasonal components are there, and there are strong seasonal component after a particular lag, then a ARIMA model might fit in. But if there are non-seasonal, it's not seasonal, and there are irregularities in the data, then basically using your AR or just an auto-regressive or an MA model might be better fit. But again, the forecast won't be that great, because whenever there are irregularities, it's always hard to forecast the output from that particular model. So I'm again going to reshare my models, the notebook screen. There are ways of checking your stationarity and autocorrelation. And the best way of checking stationary data or non-stationary data is again by taking a moving average or mean. So if the moving average is flat throughout your trend line or the time period that you picked, then you can fairly assume. And if, let's say, the deviation or the standard deviation of it is also flat, then also you can assume your uh, data is fairly stationary. But if at all some component of that becomes on later on deviates a lot, then the entire time series is also called non-stationary. So we need to understand that we pick the right time window, that we know that up till this time window the data was stationary, and from that point onward it became started showing non-stationary aspects too. So running this piece is just, I've calculated the rolling mean and the standard deviation of that rolling mean. So if you look at this plot, probably the deviation was good till 2020, but post that we are seeing a lot of deviation. So the non-stationary aspect started kicking in primarily here, and the rolling mean, it was increasing, but the deviation between the rolling mean wasn't as such that too huge. So probably post this particular period the data started become non-stationary and we couldn't see any seasonal component. This is the autocorrelation plot, and if you look at this plot, it shows some kind of seasonality. Let's say if we focus on these 2 points, post these data points, whether the trend is similar or not, that is how we gauge whether it's seasonal. So between every 2 time intervals, you can see the data points in between them, whether they show a pattern or not. Here I can see a very less pattern being followed, and obviously I think even in this data, the starting trend was a growth, and then it was kind of stagnant and then it declined. So it also shows that the initial period had a growth period, and then data points started to decline, and then the last phase of that particular was like COVID hit, and we could see a different kind of trend. But since we can see the data points in the single direction, you can assume that there is some kind of autocorrelation in this, because we are not seeing any thing on the negative side of it that balances out your autocorrelation plot. But considering it is there, we would say there is some kind of autocorrelation. The statistical test I was talking about, whether to understand our time series is stationary or not, is AD Fuller test, and this test again takes, basically does the same exercise. It has the null hypothesis is that the data is non-stationary, so whether we need to check the data is stationary or not. So you just parse your data series. It checks with the lag values what is the autocorrelation, and then basically from statistical point of view, whether your significant value of 90, here again we are taking the 95 confidence interval level, 99, 95 and 90. Even if at 90 it is like you are able to reject, then I think it's good enough for your forecasting work. But if not, then I think there is a requirement of differencing or suppressing data points which were causing these non-stationary aspect, or imputing newer data in that particular area to at least get a stationary field out. So when we ran this, we didn't get a good p-score. It is 0.19. Obviously doesn't fall in the significant range, and that's why we are calling out the data is non-stationary. So this is like, I think these are some basic steps that you should always follow whenever you're starting with any time series analysis. There are other tests also available and better visualization techniques that can help you, but from a very niche basic point of view, these are the go-to steps that you can use your time series and reconstruct it and decompose it in this way to basically get a cleaner time series output for your forecast model. Moving back to our deck again. Right. So the last section, and I think we won't be able to second. Okay, and the last section here, I think we will just be able to touch base on the forecasting techniques and why they are, what kind of forecasting techniques currently exist, which models are best fit for which kind of use cases. We'll just touch base on that and the application aspect. the hands-on session where we work around these models and how to generate a better output from these. Maybe we can have a separate session for that moving forward. Now, in terms of forecasting techniques that are out there, again, I in the previous slide I mentioned about there are univariate and the multivariate. Multivariate is whereas you have a date field, you have a met KPI that you want to forecast, plus there are other dependent variables with you that also drive somewhat of your trend with respect to the KPI that you need to forecast. So those are multivariate techniques, and they need a better model to be capture all those elements and then forecast it out. Whereas in a univariate technique, you don't need to have um, anything of that level of sophistication. Um, you can have a cleaner output prepared based on the decomposition steps that you take and how you clean them. And then the AR model technique, which is basically as per lags, how are you going to forecast? That is just the AR autoregressive way. So it takes the condition here is it should not be autocorrelated because it's taking the lag of the same data and trying to forecast what the future will look like. You can consider it is more like on a week on week change that would be there, or like if the data is weekly flighted, and if it's a monthly data month over month, what is the change, and using those components only to forecast along with the seasonality component that's always there. So seasonality along with how you project lag over like week over week or month over month or data point over data point. That's all. Moving average is the window here was, let's say the lag was 1 week. In the moving average, your window is a 4 week period. So a 4 week moving average value adjusted with the seasonality would give you a forecasted output, which is based on just how last 4 weeks have played out. There are different terminologies used for this. Some places in financial use cases, you would see it's called a run rate methodology. In some other use case, you might see a rolling mean methodology. So different names, but all are like the same technique. So whenever we try to integrate both these techniques, and so basically we have to understand all the components of AR and MA. That is why like these two models were integrated together. So autoregressive integrated moving average is two different models which are integrated and is lagged on forecasted error. So moving average model can be built on the moving average of actuals plus lagged forecasted values, lagged forecast error values as well, because it takes care of those error terms that will play out every to between data point to data point, and make sure that in the forecasted data point, those error lag values are also adjusted. So a much more closer output. But again, if there is a lot of irregularities in the data, like the residuals of the data have a high variance, then it will be again very difficult. It fits very well for the data that is stationary, not increasing sharply over time, not declining sharply over time, and it has a strong seasonality attached to it. It will work very well for that kind of data. Whereas ARIMA and S-ARIMA is nothing but when a seasonal ARIMA component is also added. We have some orders or the characteristic components in this particular model, which we will further discuss when we do a hands-on of this particular model. But just to give a gist of what it is, so we have a component called P, is the order of AR term, where the number of lags of the forecasted term to be used as predictors. So if you, let's say, want to just shift your data point by 1 week or 1 month in, let's say it's a monthly flighted data, is just give the P value as 1. It will lag predict your future by just 1 week of lag. So basically it's a month over month change that will be taken. If you take a 2 window, it'll be like a bi-monthly change that is going to address to. Then the second component is Q, is basically the MA term where the lag number forecast is taken care of. And the lag forecast error is basically the residual that plot you had. You see that plot whether lag 1 value will make sense in adjusting that or lag 3 value will make. So it's an iterative process, and that's why most of these ARIMA and SARIMA techniques take some kind of like lot of iterations together to come to that fixed order value, like order of this P, Q, and D, and then it will help you in generating the forecast. The last thing that was not there in AR and MA was the differencing. As I told you, we need to have a stationary time series. Let's say when we don't have, we give a window to which it will subtract with, and it will create the time series as stationary. So let's say there was a COVID component there. We create an we create a time series that does not have that particular COVID impact down. So let's say last year's data of the same time period we take, and we difference that, and we try to, or we impute that, and that's where it will take, not consider that COVID impact in the future forecast. So that's where we need to make sure that it's taking it. So again, the D is again the number of differencing that you want to take, could be 1, 2, 3. It's just from one data point to other data point in your time series, how you move and whether that differencing makes sense. So you'll have to run multiple iteration of this to understand whether this will work out in the use case that you are using. On the multivariate side, be I I think it will be better if we talk about in our next session, because FBprophet has a lot of hyperparameters and things that we need to talk about in detail, which are not usually even considered in the traditional univariate modeling techniques. So we'll stop over here, and I'd like to address all the Q&As that I have received so far and the other questions in the chat.
Okay, Varun. Before we will move to Q&A section, I would like to share a poll. So please, everyone present over here can go through the polls and share that. After that, we can move to the question Q&A section. Just a second. So I'll request the attendees to please fill the poll about the feedback, as it helps us to conduct more such sessions. Okay, Varun, now you can take the Q&A section. The poll has been shared, so they will be answering.
Sure. I think there is a question around ACF and PACF. So as I explained, the autocorrelation function is there to understand two aspects: whether your trend itself is autocorrelated with the lag values of the trend. If not, then it is fit for forecasting. If, let's say, the autocorrelation is there, then you see the visual plot of ACF out, and when you see if there is a periodic seasonal trend in that, like the data points are showing a pattern in that, then also it's a fit data, because there is a strong seasonality in this. So the autocorrelation might be related to the seasonal component, and that is why we uh, do this kind of a sanity check on our time series data, and it helps us in understanding um, whether this can be used for any kind of ARIMA model or AR model or MA model. So if ACF doesn't show you any kind of seasonal aspect, and the data is only unidirectional on the positive side of the axis and not on the negative side, you can say it's non-seasonal and AR or MA model. But if it is on both sides, it's seasonal, cyclic, so it's like ARIMA model or S-ARIMA model, SARIMAX model will be a better fit. FFT pack is the Fourier transform pack. It's available in the NumPy package. Fourier transform is nothing but you try to superimpose sinusoidal and cosine waves on your trend, and if it is able to fit, at what order it is able to fit, that is important in understanding the seasonality of the data. So that is, I will be sharing the data set and the Jupyter notebook post with the moderator, so they will probably help you with that. Yes, the data was of trend car sales. Let me check other questions that were in the chat. In terms of tools, both R and Python have same kind of modules and libraries for time series analysis and forecasting, but I would recommend doing it on Python, as stats modals, SciPy and sklearn have almost every functionality that need to be catered to whenever you are running a time series analysis. And yes, the notebook would have that, and it will be shared by with you by the moderator post the session, so you can take a look at that and the packages that have been used.
So Varun, we have taken the questions.
Yeah,
Okay, so I guess that's a lot. So thanks a lot, Varun. On behalf of Analytic Vidya, I would like to thank you for your time and delivering such a wonderful session. I'm sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future. So the LinkedIn profile will be given of Varun. It will be in the chat section. You can find it over there. So thank you everyone. Uh, it was a great session.